Assalamualaikum dear students. This is our next video, next problem once again having been chosen from the book Modern Physics by Kenneth S. Crane. This problem has two parts, okay, A and B. Assuming a separation of 0.193 nanometer, compute the expected electric dipole moment of NaF. Na stands for sodium and F stands for fluorine gas. Okay, sodium fluoride, not sodium fluorine. Okay, sodium and fluorine, but molecule is sodium fluorine. In the same way as NaCl, sodium and chlorine, and then sodium chloride. Similarly, potassium and bromine, but their molecule called potassium bromide. Similarly, potassium and iodine, but their combined name is potassium iodide. Okay, so chlorine chloride, fluorine fluoride, iodine iodide, and so on. Okay, basically these things are more related to chemistry, but in our physics these are also fundamentals. Okay, assuming a separation of 0.193 nanometer, nano standing for 10 to power minus 9. Okay, 0.13 nanometer means 0.193 into 10 to power minus 9 meter. Compute the expected electric dipole moment of sodium fluoride. Part B. The measured dipole moment is 27.2 into 10 to power minus 30 coulomb meter. What is the fractional ionic character of sodium fluorine? Sodium fluoride. Okay, dear students, we will get enough foundation level information from our helping tools. Okay, so now we move to our helping tools so that we may be able to solve this problem as suggested by those helping tools. Okay, helping tool number 1. Helping tool number 1. In helping tool number 1, electric dipole moment is defined, but here our method or approach will be slightly different from this expression or definition of electric dipole moment. Okay, this snapshot has been taken from some book in which this definition or expression is contained in chapter number 26, and this equation which deals with the electric dipole moment of an electric dipole is equation number 26.16. okay, that is equation number 16 of chapter number 26. Okay, so let us formally define this term. Okay, the electric dipole moment P of an electric dipole has a magnitude P equivalent to 2aq. Dear students, here two lines are parallel, which means exactly equal, and one line is above these two parallel lines, we usually treat this symbol as equivalent to, okay, not exactly equal to, uh, uh, is defined as. This symbol is also um, meant as, is defined as, okay. So electric dipole moment P is defined as 2aq, okay, where 2a is the distance between the charges q and minus q. The direction of the electric dipole moment vector is from the negative charge toward the positive charge, okay. We will not exactly follow this equation, but our philosophy will exactly of this nature, okay. Now we move to helping tool number 2, okay. Helping tool number 2, this is a table, and table is about properties of some ionic diatomic molecules, okay. 1 2 3 4 5 6 7 8 9. This table contains 9 rows, and second row is our concerned information, okay. NaF, sodium fluoride, its dissociation energy is 4.99 electron volt, while its equilibrium separation is 0.193 nanometer, okay. Dear students, this value is given in the statement 0.193, okay. So we do not need this table, but benefit of this table is just to develop a sense of confidence and satisfaction in us that such value is usually taken from such tables, which sometimes occur in between the chapter and mostly occur in appendix at the end of book, okay. So dear students, this value, that is sodium fluoride, whose dissociation energy is given as 4.99 electron volt, and equilibrium separation is 0.193 nanometer. We once again go to this, okay. We have once again shifted to a problem in which it is given that assuming a separation of 0.193 nanometer, okay. So dear students, this value is contained in the problem. We do not need that problem or that table, but purpose of including this table in our helping tools or in our toolkit is just to develop a confidence or satisfaction about this value, that which is given in row second row, okay. So suppose in some other problem this value in place of sodium fluoride some other molecule is taken and its equilibrium separation is not given, then definitely we will consult such tables, okay. This table has been this table has been chosen from some book in which this table is contained in chapter number 9 of that book, okay. That is why this table has number table 9.5, okay. That is to say fifth table of 9th chapter. In other books this table may or may not exist, and some of these molecules may be present and some other molecules might be included in this table as per discretion of the author of the book, okay. Now, the same helping tool, that is tool number 2, is here once again given in some alternate form. Okay, we may say that it is another version of table number 2. Okay, helping tool number 2, which is basically a table. Okay, table number 9.2 or 9-2, dissociation energies ED and equilibrium separations are not for several ionic molecules in the gaseous state. Okay, dear students, here once again, second row, dissociation energy is given as 5.34 and equilibrium separation is 0.193. Okay, what is the difference between these two? Oh, okay, yes, RbCl and RbCl. Yes, one difference is that in this table last molecule is RbCl, while in alternate version of this helping tool, last molecule is CSI. Okay, so definitely when we choose a table from some other book, then definitely some change might be a necessary part of that table. Okay, next table helping tool number 3. This is again a table, and this table has been included in our toolkit several times in our previous videos, in our previous problems. Okay, so because this table has been included in several previous problems or videos, so we will not give enough time to discuss this table. Okay, so discussion or explanation of this table is skipped for the time being. Okay, now helping tool number 4, and this tool has been given once again in two versions. Okay, this is first version of this tool, and then the next version of this tool will also be almost same thing. Okay, this tool says that fractional ionic character, which is asked in the problem statement. Okay, fractional ionic character is equal to P measured over Q ReQ. P stands for electric dipole moment. Okay, measured electric dipole moment divided by Q charge and R separation distance, equilibrium separation. Okay, EQ stands for equilibrium separation, or EQ, or yes, its alternate version is given in this. Dear students, in this position both of these versions are being shown. First version has been given equation number 9.5. Actually, while its alternate version, fractional ionic character P measured over QR equilibrium EQ. Okay, yes friends, this helping tool, this snapshot has been chosen from the same book which we are following. Okay, which we are following means Modern Physics by Kenneth S. Crane. Okay, this snapshot has been chosen from the book Modern Physics by Kenneth S. Crane, and actually it is not equation number 9.5. It is this this snapshot has been selected from the book Modern Physics by Kenneth S. Crane, and in the end of ninth chapter a summary is given. Okay, from that summary this equation has been chosen or selected. So this 9.5 indicates that chapter number 9 has several topics, and this is actually fifth topic of this chapter. Okay, this is not equation number 9.5. When we will go to fifth topic of ninth chapter, then this equation will appear there, and at that place its equation number will be definitely different from this. Okay, so anyhow we move forward. Fractional ionic character P measured, that is to say electric dipole moment, measured electric dipole moment divided by Q equilibrium separation, that is REQ, where EQ is written as a subscript of R. This is 9.3 and this is 9.5. Okay, now we come to solution. Okay, actually dear students, I am thinking that perhaps it may happen, I do not remember very clearly, that perhaps because this is also chapter number 9 and this is also chapter number 9, so it is possible that both these versions of tool might be selected from the same book, Modern Physics by Kenneth S. Crane. One snapshot may be taken from the equations which are given within the chapter, and one equation or result may be that which is contained in summary at the end of ninth chapter. Okay, so anyhow it is a quite less important thing. Okay, now we come to its solution. First we will solve part A. Okay, dear students, for solving part A, first we develop a foundation, okay, so that we may put the concerned values in that equation or expression or result, and then we may reach our solution. Okay, solution of part A, we know that electric dipole moment of an ionic molecule is given as P equal to Q R EQ. Equilibrium separation REQ. Here EQ is written as a subscript of capital R and EQ stands for equilibrium. Okay, this is given equation number 1. This is given number 1 to this equation. Okay, where Q electronic charge, where Q is equal to E is equal to 1.602 into 10 to power minus 19 coulomb, and REQ is the equilibrium separation of the ion. Okay, yes students, we may observe this fact that when we consult various books to solve such problems, we will see that some books use symbol Q for charge, while some other books use the symbol E, because here it is, this Q is electronic charge on an electron. Okay, so it does not make very much difference whether we use small q or whether we use small e. Okay, and this value, that is 1.602 into 10 to power minus 19 coulomb, is given in tool number 3, which a comprehensive table had a lot of physical constants, and we had skipped that table because um, we had included that table in a large number of our previous problems or videos, so we did not give any time regarding the explanation or discussion of that table in detail. Okay, so this value is taken from that table which we skipped, and Req, where Eq is written as a subscript of R, is the equilibrium separation of the ion. Okay, next. Now we are going to put values in equation number 1. Okay, using Q equal to 1.6 here. Okay, here we assume that a Q is directly given equal to this and E is not used. Okay, so from here Q is equal to 1.602 into 10 to the power minus 19 coulomb. Okay, this, and R EQ, where EQ is written as a subscript of capital R, that is equilibrium separation, is given as 0.193 nanometer. Okay, this value, dear students, this value is given in the statement equilibrium separation, and this value is also given in two tables which we introduced as a part of our toolkit. Okay, that tool had two alternate versions. Okay, but in both versions this value was the same. Okay, so this value is not only given in the statement but also given in two tables which we have shown in our toolkit. Okay, using these two values, equation number 1 becomes electric dipole moment P is equal to this into this. Okay, what we have done, we have just put the two values, this value and this value. Okay, and the next remaining is only simplification. This is not disturbed into 0.9. Yes, in this step, what we have done, we have replaced nano by 10 raised to the power minus 9. Okay, we can do it because nano is equal to 10 to power minus 9. So here n has been eliminated and 10 raised to the power minus 9 has appeared. Okay, in the next step we have multiplied 1.602 with 0.193. Okay, multiplication of these two values, okay, will become 0.309186 into 10 to power minus 28 coulomb meter. Dear students, actually this is 10 raised to the power minus 19 and this is 10 raised to the power minus 9. Okay, so according to mathematics basic principles of multiplication, these two terms will be converted into 10 to power minus 28 coulomb meter. Dear students, to this extent our problem has been solved exactly, but there are some formalities, there are some fashions which we usually prefer to adopt. Okay, so dear students, this result is exactly acceptable and correct, that is 0.309186 into 10 to power minus 28 coulomb meter. But now we are going to adopt that fashion which mostly appears in books of physics. Okay, what pattern? The pattern is that this quantity is usually in terms of 10 raised to the power minus 30. Okay, so in order to convert this figure into 10 raised to the power minus 20, minus 30, we will convert this figure into 3. Oh yes, we have not we have taken only in next step, we have changed it into 3 point. Instead of 0.309186, we have written it as 3.091, and hence minus 28 has been increased to minus 29. And in the next step, we have rewritten this expression in this form: 30.9186 into 10 raised to the power minus 30 coulomb meter. Okay, so dear students, this answer is also exactly acceptable and correct, but next two steps are just to adopt a fashion of physics which prevails in the books of physics, and this is the no so sorry oh yes yet part B is remaining. Okay, this is part A has been solved successfully. Now we move to part B. Okay, part B, dear students, is about fractional ionic character. For this purpose, we had introduced a helping tool which had two versions. Both versions had equations of the form 9.3 or 9.5, and about this helping tool, I had expressed my opinion that these two versions might be taken from the book which we are following, that is Modern Physics by Kenneth S. Crane, and one version might be given in between the chapter, and other version might be given at the end of the chapter in summary, because in the end of each chapter a summary is given, and in that summary conclusions are given topic wise. Okay, so this expression has been previously shown in our toolkit. Okay, so dear students, electric dipole moment measured is given in the statement. Okay, 27.2 into 10 to power minus 30 coulomb meter. We once again move to our statement, and it will be clear that, okay, yes, dear students, the measured dipole moment is 27.2 into 10 raised to the power minus 30 coulomb meter. Okay, so this value which is given in the statement has been used here. Okay, this is solution of part A, which was completed, and now we have started part B. Okay, this value is given in the statement, and this value is that value which we have calculated a little earlier. This value 30.9186 into 10 to power minus 30 coulomb meter. Dear students, here, because P is equal to this, okay, P is equal to Q R EQ, that is equilibrium separation or equilibrium. So we will use this value P equal to this. Okay, this value in place of Q R EQ. Okay, this value is given in the statement. This value is given in the statement. And this value. Okay, here actually, dear students, we have once again taken separately first value of Q or value of small e, electronic charge. Okay, and then R EQ, equilibrium separation R, its value was given as this. Okay, in place of, we can skip this step, and in place of this we can directly write this figure, okay. But here we have not adopted this facility. Actually this is a facility, that value of um, that value of q or eq is given, okay. This value is given, but we have not availed this facility, and we have put values of these two as separately, okay. But despite this, result will be exactly same, okay. In the next step we have not disturbed this. Dear students, actually this column meter, this is column, this is meter, okay. This column meter will be cancelled with c, will be cancelled, column will be cancelled with column, and meter will be cancelled with meter, okay. Column meter has been eliminated from our solution, and hence our result will only include nano n, small n, which is equal to 10 to power minus 9. So in other words, we have no unit, okay, only number is involved, okay. This divided by this into this. We have not disturbed 10 raised to the power minus 19, we have multiplied this with this, so this result has come, okay. Actually this was 30.9186 into 10 raised to the power minus 30, but here in place of 30 we have used 0.30, okay. Anyhow, dear students, in the next step what we have done, we have solved this thing, that is 27.2 divided by 0.309186, and its result has become equal to this 87.97 into 10 raised to the power minus 30, this given. And this 10 raised to the power minus 19, this is in the denominator, we can shift it into numerator, and after being shifted to a numerator, its sign will become positive, okay. 10 raised to the power minus 30 into 10 raised to the power plus 19 into 10 raised to the power 9, because nano is dear students 10 raised to the power minus 9, 10 raised to the power minus 9, okay. Dear students, to this extent this is same. Oh yes, dear students, actually there is a minor mistake, minor mistake. No mistake, dear students, no mistake, okay. What we have done, we have shifted this to a numerator, due to which its sign has become positive. Similarly, this n is 10 to power minus 9, but this is in the denominator, and we have shifted it to a numerator, okay. So due to its shifting to a numerator, sign of this has become positive and sign of this has also become positive, okay. So that is why 10 raised to the power plus 19 and 10 raised to the power plus 9, okay, these two will contribute to 10 raised to the power 28, okay. So 10 raised to the power 28 and then 10 raised to the power minus 30, so it means 10 raised to the power minus 2 will prevail, okay. Out of 10 raised to the power 30 minus 30, 10 raised to the power plus 28 will be subtracted, and we will be left with only 10 raised to the power minus 2, and this 10 raised to the power minus 2 uh, will change this figure to 0.8797. Okay, 0.8797, we have rounded it to 0.88, because dear students, if after 7 the digit is greater than 5, then we have an option to increase this by one number. Okay, so instead of writing it as 0.8797, we have rounded it as 0.88. Okay, so when this has become 0.88, then we will write that this implies, this symbol is, this implies that sodium fluoride is 88% ionic. Okay, because in percentage we have to multiply with the 100, so I think it is clear. Okay, there should be no doubt in it. This 0.88 has been taken as 88%. So our result of part B is that sodium fluoride is 88% ionic. And this is the end of our problem, and this is the end of our video. Till next video, Allah Hafiz.